So next up we have Josh Thia, and Josh is from my group in Melbourne University, and he's been doing some really exciting work on novel approaches to looking at resistance and looking at the genetic basis of resistance. So this is really about thinking about the future. Josh.
Oh, thanks, Ari.
Right.
Cool. Hello? All right. Like Fran, I also... Is this on? Yes? No? Cool. All right. So it's great to be able to present to you today at the Crop Protection Forum. So thanks for having me along. Today I'm going to be presenting some work that we have been doing on predicting the risk of pesticide resistance in agricultural arthropod pests. And what I don't want this talk to be is one where you think, ugh, mass, gross statistics. But what I want you to take away from this talk is some of the exciting advances that we've made on being able to predict which species and which chemical modes of action may be most at risk of evolving resistance, and then how this can be sort of used to inform proactive management strategies. But then also, I want to highlight some of the challenges that we have in this predictive modeling space as well, and to highlight some of the future directions that we may want to take this work. And even though I'm presenting to you today, this work has been contributed to by a bunch of different people. So there's the crazy cast of characters, so thank you to all of their support. All right, so, just to set the scene, we don't like pesticide resistance because a lot of time and effort goes into developing chemical products, and then when we overuse these chemicals and resistance evolves, we lose that potential control strategy. And then when pests, start evolving and accumulating too many resistances, we then end up with a potential situation where we have no efficacious way to control a pest. And then we have to go back to the chemical companies and say, yikes, we need more chemicals. And they then need to go through the long, arduous, expensive process of developing more chemicals for agriculture. So in Australia, a lot of, as Paul sort of highlighted earlier, a lot of our major pests are accumulating resistances at a much more rapid rate. So actually, I'm just focusing on, insect and mite pests, but the similar is with fungicides and herbicides. And so anyway, these are some of our major pests in Australian agriculture, and this work just highlights that there has been this acceleration in the number of pesticide resistances that we've seen here in Australia. And so the accumulation of pesticide resistance sort of worries us on two fronts. We have sort of number one, resistant species accumulating more and more resistances, which makes them increasingly harder to control. But then we have susceptible species that also start popping up out of the blue with resistance. And this means that, on the one hand, we have really resistant, highly problematic species, and then we are also adding new species that we need to consider in our pest control strategies. So when we are thinking about resistance management, we can either go about this in one of two ways. We can either think about it as a reactive approach, or we can think about it as a proactive approach. Now on this slide, what I've got illustrated is this resistance evolution cycle, and it starts off with our crop being infested with a pest that we're not so happy about. We then go and apply a pesticide to that pest, and then that application of pesticide imposes selection on the population, and it selects for individuals that carry genetic variation that makes them more tolerant or resistant to that pesticide. They then increase in frequency in that population, and then we then try and apply more pesticide to kill them, but that's ineffective. And then we just go around and around this loop, selecting for more and more resistant individuals, and then resistance spreads until we get a point where we have a control failure. So if we take a reactive resistance management approach, we are coming in at this control failure stage. So we're identifying resistance after it evolves, And the point of this management strategy, this management comes in after resistance has become an issue. And at the early stages, the aim is to determine the magnitude and the distribution of resistance in our populations, with the goal of reducing its spread and decreasing the prevalence of resistance in those populations. But the issue is that once we've got very widespread resistance, that genetic variation is already in the population. So it can be really hard to completely remove resistant carrying genes from the population, and then there is always the potential that we can lose a chemical mode of action. Now, in contrast, a proactive management strategy happens much earlier. And the key for a proactive management strategy is that we are identifying the risk of resistance before a control failure occurs. And so the point of this is that we want to identify the risk of resistance before resistance is an issue. And a part of a proactive management strategy is making decisions on how to invest and monitor for resistance in order to make long-lasting control plans for maintaining chemical modes of action and preventing the evolution of resistance altogether. So, in order to have a successful proactive management strategy, we have to really address the question of how much selection is being imposed on pest populations, and then therefore what is their resistance risk. And you can sort of break that down into sort of these three key questions. We first want to know how much pesticide is being used in agriculture. Secondly, we then want to know how that usage then translates into the risk of a particular pest evolving resistance to that pesticide. And then ideally, what we then want to then move toward is asking, where is pesticide resistance risk greatest? Now, these three questions are key, but it's really difficult to actually address them properly because the data that we need to address them is either really inaccessible or it just doesn't exist whatsoever. But the point of today's talk is to highlight how we have been able to make advances on addressing these first two questions using sort of a slightly unconventional and novel approach by using publicly available data. Okay, so we'll start with the first one. How much pesticide is being used in agriculture, and therefore, what is the selection pressure for pests to evolve resistance? Now, okay, so this data, actually, I'm going to go back. So this data doesn't readily exist in Australia, but in other parts of the world it does because they have very strict and regulated frameworks by which farmers have to report how much pesticide is being used. So in those instances, you can get a very good gauge of the pesticide usage and how much selection may be in the agricultural systems. But here in Australia, we don't have that. So what we need to do instead is we either have to, one way is that you could rely on survey data and then people sort of self-report in a sort of an unstructured way about what they're using. Or alternatively, we can try and find measures that correlate with the amount of pesticide usage and therefore can be used as sort of an inference of selection in the field. And so the way that we decided to try and tackle this issue of identifying a correlative measure of pesticide usage is through using pesticide product registrations. So actually, I was really excited, Fran, when you showed that graph at the beginning of your talk, how there's sort of pesticide usage increasing and more registrations for different pesticides. And so pesticide registrations are they're publicly available data in the APVMA database. And so our hypothesis is that, we can use these product registrations as sort of a proxy for the amount of pesticide usage and selection in agriculture. And our rationale is that, when a pesticide product when a new chemical is first introduced, it's not very highly registered and it's not very popular and it's not very accessible. But as more and more product registrations become available, pesticides then start to increase in their availability and their popularity, and this therefore leads to greater use in agriculture. This greater use then, in principle, probably leads to greater selection for resistance to that particular pesticide chemical. And then ultimately, as resistance starts to accumulate in the populations, this leads to less effective control and more pesticide use, more registrations, greater availability, more use, etc. Completing, doing this cycle again and again. So in a nutshell, the hypothesis is more regos, more usage, more selection. So we wanted to test this hypothesis to try and validate whether or not we can use pesticide product registrations as an estimate of the amount of pesticide usage. And so we did this by fitting this model, where we have pesticide usage is a function of the product registrations for different chemical modes of action, and also some other agricultural factors. And the only reason why we were able to fit this model in the first place is that we were able to access some usage data that Bayer obtained, that Bayer Crop Sciences obtained in a survey of different crops, and they provided us that information, which we were able to marry up to product registrations in the APVMA database. And so, one other thing that I want to highlight is that this data set that Bayer provided was not just for insects. It included chemicals for herbicides and fungi as well. So what we're doing here is looking at all the different types of chemicals and how the pesticide registrations for all those chemicals potentially are correlated to their usage for all the different pest categories. And what we were really excited to find is that our hypothesis was indeed true. There is a positive correlation between the amount of pesticide being used in Australian agriculture and the number of pesticide product registrations. And so this came out in our paper, recently led by James Mayno in Crop Protection. And so this is really exciting because it means that, even though we don't really have a great way of actually getting quantified estimates of pesticide usage, we can use product registrations to potentially infer selection to herbicides, insecticides, and fungicides. So we wanted to run with this information to try and address this second question of what is the risk of pesticide resistance evolving in Australian agriculture? And in this case, we specifically focused on insecticides. So in this case, we built, in this follow-up investigation, we built a model which was looking at the risk of resistance as a function of the pest's ecology and the selection pressure, which breaks down into these components. So with resistance risk, we mined the arthropod pesticide resistance database for records of resistance in different pests. We used the number of plant host families and the number of generations as our ecological traits that contribute towards an increased risk of resistance. And then for the selection pressure, we used the pesticide product registrations from the APVMA. So in total, what we did is we estimated the risks of resistance for 209 different insect or mite pest species from 65 different families to 27 chemical mode of action groups. An informed threshold level by which we're going to say that this is a non-negligible risk. And we did that by looking at the upper limits for susceptible pests and modes of action to define that threshold. As a caveat, this model is only looking at the risks for pests at an Australian-wide level and across different industries. So there are some nuances that could increase or decrease the risk depending on how you look at it. But at this point, we're just interested in getting broader insights into resistance risk. And then finally, another thing that our model does not account for is the potential for off-target selection. And so this off-target potential can probably increase a lot of the risks that we'll present today. And I know Lisa Bird is going to be talking more about off-target selection. So I just thought I would, start wrapping up with a little bit of an insight into what these models are showing us and how we might try and interpret their results in the context of proactive resistance management. So what I have here are the risk outputs for diamondback moth and Helicoverpa armigera. And on the x-axis, what we have are the different chemical modes of action. And on the y-axis, we have the model's predicted risk for that species and the chemical mode of action. That black horizontal line running through the plots, that's the threshold level. So anything above that level is considered a potentially non-negligible risk. Now, the bars are colored with respect to whether or not that pest has resistance in Australia. So those red bars are for resistant chemicals in those species, and the blue bars are for currently susceptible chemicals. So the thing that we are most interested in from a proactive management perspective are the blue bars that jut above that horizontal line. Okay? So one thing that really jumped out to me when looking at these resistance predictions for these two pests are the risks for the group 5s. Okay, so we've got here and here. And so the group 5s are your spinosins, so that includes spinosad and spinetoram. And the reason why these this group 5 chemical class is really important for these two lepidopterans is that, well, it's it's one of the few chemicals left in these pests that that hasn't yet evolved resistance. And it's also a really important chemical with respect to IPM because it's much more selective towards lepidopterans and it's less impactful on natural enemies. So the fact that we have this group 5 peaking up above our threshold suggests that we might want to start thinking about, screening and monitoring for group 5 resistance in field populations of these lepidopteran. And actually, it was pretty funny this morning because Paul highlighted that there's been recent discoveries of group 5 resistance in diamondback moth in WA, which I didn't know about. So that kind of, if that's quite serendipitous, really, for this talk, but it's something that we should be thinking about. The other one here that sort of really jumps out is the prediction risk for group 19. So this is for amitraz. And so amitraz is not really used, it's not used in the grains industry for the control of Helicoverpa armigera, but there are lots and lots of products of amitraz used in the cotton industry. So that's why you're getting this big spike here for Helicoverpa armigera to amitraz. And then just finally, here are the results for the red-legged earth mite. So as Paul highlighted earlier, red-legged earth mites already have resistance to organophosphates and pyrethroids. And then the only two other chemicals that we have left for red-legged earth mite control are neonicotinoids, the group 4A, and the 12A, which is diethenthiourone. What we can see from this graph here is that the predicted resistance risk for 4A is starting to peak above that line. So if we had our proactive resistance management hat on, we would then maybe start thinking about having a conversation of whether we need to think about our use of 4A in red-legged earth mite control. So just to wrap up, I just want to highlight some of the successes, of our project. Firstly, we were able to identify a measure of pesticide usage using publicly available data. And so this is really exciting because this is sort of the first time that, we've been able to, get a handle on the pesticide usage and potential selection on arthropod pests in Australia. And this is also translatable to weeds and also to fungi. We then use this information to then build models of the resistance risks to different pests and chemical modes of action. And then in combination, these two things are potentially setting a good foundation for proactive management initiatives using a modeling-based approach. So the next steps to this work, it would be really great to get the results curated and set up in some sort of publicly available platform so that they become available to growers and to agronomists so they can make decisions about what chemicals they're using with respect to the overall risk that these chemicals might pose for resistance in those pests. But there are also some other things that we also need to consider to make these models better and improve the robustness of their predictions. Second, one of those things is identifying local risk factors for resistance. And that's because, while our models are great for getting sort of a general overview of resistance risk, what is really important from a day-to-day management perspective is what's my local risk here right now. And so we do not yet have a good way of estimating, the local selection pressure and the local risk. So this is going to be a major challenge that we somehow need to overcome, but that's a future me problem. Then the third one is also incorporating off-target selection into our risk predictions. And the reason why that's important is because, we have communities of pests. We're not treating pests in isolation. So anytime we apply a pesticide, we are selecting for resistance in a whole raft of different species that are co-occurring in a paddock. Right, and just to wrap up, I've got a bunch of organizations to thank. The arthropod pesticide resistant database for access to the resistance records, the APVMA and Bayer Crop Science, and then finally, thank you to the GRDC and the University of Melbourne for supporting this work. And at that, I'm happy to take any questions. Thank you for listening.